Hi, welcome everyone. Welcome to the course and introduction to statistical mechanics in soft and active matter systems. So far, whatever we studied in a system where there is, uh, you know, the system is a passive system. That means there is no uh, breaking of detail balance. There is no self propulsion like this. So, in the last 1.5 decades, there is a growing interest in a field called active matter. So where there is external driving, the system is driven um, internally or externally, apart from the thermal fluctuations, and out of that there is a system called active Brownian particle, which is also called ABP. So this is a system of cell propelled system. So here, so first, this system is a self propelled system. So what it does, it consumes energy from the environment and does some dissipative work. So this is a current hot topic in the field of software and active systems, and you can, if you see the papers, there are paper popping out, 2 or 3 or more than that per week in archive or in another journal. So these are self-propelled system. Since this is self-propelled, so this is torque free and force free. Okay, so basically what is happening here is there is one particle. It has a self propulsion part, which is manifested by a constant velocity or speed, and so it changes directions, and it changes direction by orientational diffusion. Orientational diffusion. So basically, so there is particle. So we know that a particle, if there is some asymmetry, so it is also, there is some orientational diffusion in the particle, and it is governed by orientational diffusion equation, and we solve for that. So basically, if you write, so the Langevin equation for this, so I'm not going into the main details, I'm directly going to the Langevin equation. So it will be then, so So let let's say it has the inertial force is very much negligible. So at that limit, at the limit where inertial force vanishes, there we can write the Langevin equation for this system for the translational degrees of freedom. Translational degrees freedom. So let's study for 2D system. It is given by dx dt is equal to v cos phi plus eta xt. So this is thermal fluctuation, and dy dt v sin phi. So this is phi of t plus tau yt. And here these are the random velocities. Eta x t prime is 2d delta t minus t prime, and eta y t prime is 2d delta t minus t prime. So here we have taken a spherical particle, that's why it's vertically symmetric. Okay, so that is the equation. And phi is governed by like free Brownian motion in these degrees of freedom. So this will be d phi dt, like eta phi t, where eta phi eta phi t prime is 2 dr delta t minus t prime. So here d is translational diffusion constant, which is given by d as kbt by gamma, which is kbt by 6 pi eta a. A is the radius of the particle, and dr is rotational diffusion constant, which is d by kbt by eta pi 8 pi eta a cube. So if you see, this has a unit of L square t minus 1, and this has a unit of t minus 1. Okay, so that's the main thing about this. So here you can see now this, the change in orientation is smooth, and it is governed by the orientational diffusion. And there is one more active particle. So a special, an example of this active Brownian particle is called genus colloids. So there is like there is a colloid like this, and at one surface it is being coated with some platinum and all this, and there can be, by some external agents, you make a certain asymmetry that it self propels in some direction with velocity v. So you can see here in the Langevin equation, only the thing that is changing, so you are adding some self propulsion part to this Langevin equation. Okay, and v is the self propulsion speed. Okay, so that is the active Brownian particle. There is also a certain class of particle is called run and tumble particle, which is called RTP. So this is a special class of particle. Here it is different from the active Brownian particle. So so there are specific kind of bacteria. So let's say E. coli, Salmonella, this kind of bacteria. So they show RTP kind of dynamics. What is that? What is the thing? So so they, like, they almost run in a straight line, then they stop for a few minutes, and then again they take another route, then again they take almost straight path and again take another route. So but this is you can sense like this, but here the change in direction is abrupt. Okay. So the run state, so basically run moving in almost straight path, which, you know which is happened by the, different ways. Let's say for E. coli bacteria, it happened by using the synchronized motion of the flagella, and they make a spindle kind of a thing, and it propels in a directions. Okay. Then their tumble, it's like sudden change in direction, and it happens in smaller time. So let's say if the mean runtime is 0.9 second, the mean tumble time is 0.1 second. So it changes its directions very fast and rapidly, and then again it takes a new direction and follows the direction for the for few minutes. So let's say this is run, then again it changes direction, this is tumble, again run. So it sort of run states are punctuated by the tumble states. Okay, so this kind of motion is called run and tumble, and those particle which shows this kind of dynamics, they are called run and tumble particle. Here also you can write that it shows, like, here the model's little bit complicated because it's kind of, you can think of it as two state system where it, like where it is translating the Lagrange equation, but translation motion is almost same, but the orientational change is quite different. So here change in orientation is abrupt and discontinuous. Okay, so that is that. So now, so this is that is the difference between run tumble and active Brownian particle. So now, in these coming lectures, we will talk about what is like we will derive, mean square displacement, mean of or different moments for active Brownian particle in details. So we will study in our this lecture the active Brownian particle in the details. So let's study active Brownian particle in details. So we know those equations. Now you are then now you are, so if you take this thing, then it becomes dx dt is equal to v cos phi, which is also t, plus eta x t. So now if you do the integration, then x naught x dx, it becomes t naught to t v cos phi dt plus t naught t eta x t dt. Now if you integrate this, then it becomes xt minus x0 is equal to 0 to t v cos phi 1 or phi of t1, let's say was phi 1 dt1, okay, plus 0 to t eta x t1 dt1. So basically here we will use, so this is equation number 2, equation number 1. So basically what we are using is phi of t1 as phi 1 and phi of t2 as phi 2. So we are using this nomenclature here, okay. So that we will use throughout this derivation, okay. So now let me go into the details, okay. So basically if that is the case, then it becomes so from here it follows from here it follows that x of t minus x of 0 whole square. So we will calculate the mean square displacement here. So here it becomes, so now we have to integrate over two time lag values, right? 0 to t dt1, again 0 to t dt2, if you take average, then it becomes cos phi 1 cos phi 2 v square, because v was constant, and the second term is 0 to t dt1, 0 to t dt2. Eta t1 eta t2. So basically now we have to solve this. Okay. Similarly, if you write similarly by following, similarly you can write yt minus y0 is equal to 0 to t dt1, 0 to t dt2, dt2 sine of phi 1 sine of phi 2 square plus 0 to t dt1, 0 to t dt2. So it was eta x, eta y 1, eta y t2. Now if you substitute these two terms, let's say you term this as a.2 and you term it as a.1, similarly b.1, b.2. Similarly, average of this becomes 2d delta t1 minus t2, and this becomes 2d delta t1 minus t2. So a2 and b2 are similar, so we will calculate that later, because that will give the same this thing. And you can also promptly say that what will be this value. Okay, so let's first solve this a2 and b2, otherwise, so a2 and b2 are same, right? So basically, since the particle is spherical in shape, a2 and b2 are same. Okay, so let us calculate let's say a2. If we calculate a2, we'll get the b2 thing also. Okay, so This is same as, like, we have solved this thing, right? We have solved this problem. So then just few lectures back in the Brownian motion, 0 to t dt2, this 2d delta t1 minus t2. So to do this is, like, if you take two region like t1 and t2, and if you take this graph which is t1 is equal to t2, so taking one half will solve the other half. Okay, so that's why we will solve for one half and take the multiple of the, well, twice of the that. So let's say we are solving for, let's say t1, so t1 t2, sorry, so t1 only can take, let's say, lower half we are calculating. So this will be dt1 2 delta t1 minus t2. So then it will follow so 2 of 0 to t d2 t 0 to t, zero to t1. Now this t1, sorry, this t2, this t2, we can calculate this t2. T2 can be from 0 to infinity. So then this limit t1 will be 0 to infinity dt1 2d delta t2 minus t1. Now for an half space, this become 4d times half 0 to t dt2. Okay, and if you do this, then it becomes 2d t. Why is it so? Because since 0 to infinity dt delta of t, that becomes to be this will be half of minus infinity to plus infinity, because you know this thing, because delta function is a even function. Okay, so now we have got a2 and b2 value. So this will be the integral of a2 is equal to b2. So now to know, to get a1 and b1, we need to calculate this correlation, cos phi 1 cos phi 2 and sin phi 1 sin phi 2. So we will do that. So think about it for 1 2 minutes. So now we need to find this autocorrelation cos phi 1 cos phi 2. Now to find that, what we need to know is about the transition probability density of orientation. Okay, so now the transition probability density of orientation is P of phi t is written as P of phi t starting from phi naught at t naught. So that is the probability, and you can write it as, since this is simple, you know, Brownian motion Brownian motion in orientational degrees of freedom. So we have calculated this. This will be the form 4 pi dr t minus t naught into exponential of minus 1 by 4 dr. So here we have used dr, but you can written as, this is dr, small dr. So exponential of minus 1 by 4 dr phi minus phi naught whole square divided by t minus t naught, like this. So you have seen this for Brownian motion, there phi naught was 0, so it was x square. So you have seen like this 1 by root over of 4 pi dr t minus t naught, or t e to the power minus 1 by 4 dr phi minus pi square by t 4 dr t, because you have also seen this in random flights, right? Now if this is the expression, this is equation 2, let's say this is equation 4 and equation 4, okay, and this is 3.1 and this is 3. Okay, so now calculate average of cos phi first. So the average of cos phi of t, or we can call it cos phi, its average in this system, it should be written as minus infinity to infinity plus infinity d phi cos phi p of phi t, right? Now that actually becomes as, let's say, like this. So let's say you change the variable, change the variable like this. Let's say we're changing the variable. So say from phi you are changing to phi prime, which is phi minus phi naught divided by root over of 4 dr into t, 4 dr into t. So you are changing to this. Okay. So now basically you are making it as phi minus phi naught into a. So your a then a where a is equal to 4 dr t into half root over of this. Then this your equation 5 can be written as equation 5 is written as minus infinity to plus infinity. So if that is the case, then d phi so that is the case. So d phi prime is equal to d phi by a. So a d phi prime and cos of, so your phi, so there will be a phi prime plus phi naught. You are just changing the you are just changing the variable minus phi prime whole square. Okay. So now if you do this, then it becomes minus infinity to plus infinity, minus infinity to plus infinity, a d phi prime cos of a phi prime cos of phi naught e to the power minus 5 prime square minus infinity plus infinity a d phi prime sine of a phi prime into sine of phi naught e to the power minus 5 prime whole square. Now this term should be 0 because this is odd in term, since sine a phi prime is odd. This will be that integral will be 0. So now if you take this as an integral I, then this I becomes this I then becomes minus infinity to plus infinity t5 prime t5 prime cos cos a5 prime, because everything a cos phi naught is constant, and e to the power minus phi prime whole square. Now if you try to do this, then we will do the following thing. So dia is then dda minus infinity to plus infinity t5 prime cos of a phi prime e to the power minus phi prime squared. So now will it becomes dda of this which in return give minus, because only thing is cos a is this one, so this will become minus infinity to plus infinity d phi prime sine of a phi prime times phi prime to the power minus prime high square. Then we can write this term as, if you take the d of this will be half of e to the power minus phi prime square, because you can write like this, minus infinity minus half to plus infinity sine of a phi prime d of e to the power minus phi prime square. Why? Because since d of e to the power minus phi prime squared gives you e to the power minus phi prime squared minus 2 phi prime d phi prime. So that's 2 is accounted by this half. So now if you do the integration by parts, then it becomes half sine of a phi prime e to the power minus phi prime squared at minus infinity to plus infinity minus half minus infinity to plus infinity e to the power minus 5 prime squared d of sine fi prime. Okay, now this becomes 0 because minus infinity to plus infinity, that's it's squared, it will be always positive, and since it is infinity, so it will be 0, right? So basically you are getting back to this equation, which is in turn give you minus so d of this will give you a, so a by 2 minus infinity to plus infinity d5 prime e to the power minus 5 prime squared cos of a5 prime this. Now this was the I, so then this becomes minus a by 2 I. So basically you will get then di by dA is equal to minus a by 2 a. Okay, so basically now we also know we also so basic so here we are doing the calculations from scratch. Okay, so please follow this. So we also know that if we know f prime a is equal to minus a by 2 fa has a solution in the form of f of a constant c e to the power minus a square by 4, and f of 0 is root pi, because f of 0 is I of 0 is then minus infinity to plus infinity. Now f of 0, you substitute this here, f is I, so substitute a is equal to 0, that means this is 1 e to the power minus pi square at d5. Then it becomes d5 into e to the power minus 5 prime squared, which is root pi gamma in Gaussian integral. Okay, so now we got this. So this c is then this thing, so I then becomes I, which is d5 prime minus infinity to plus infinity d5 prime cos of a5 prime e to the power minus 5 prime squared, that becomes root pi into e to the power minus a squared by 4, and we took a as 4 drt to the power root. So then so basically it becomes then is equal to root pi e to the power minus drt, since a was root over of 4 drt. So we did that. we have used this. So from here now we can write summation of a average of cos phi of t, that becomes minus infinity to plus infinity d phi cos phi e to the power minus phi minus phi naught whole square divided by 4 drt into 1 by root over of 4 pi drt. Now integration of this will become, so there was a cos phi naught, was there, a cos phi naught was there, so a cos phi naught was there, that should be the common outsider. So if you write that, then it becomes, using the formula above, become 1 by root over of 4 pi drt times a cos phi naught into root pi e to the power minus drt. A is root over of 4 dt, 4 drt, so then it becomes 1 by root over of 4 pi drt into root over of 4 drt into cos phi naught root pi into to the power minus drt. So this cancels out and it remains cos phi naught e to the power minus drt. So from here you can get, basically you are getting average of cos phi t is cos phi naught to the power minus drt. Now if you do the same thing, now this general form of this, now general formula of this expression, minus infinity to plus infinity e to the power minus x square cos bx plus c dx is equal to root pi e to the power minus b square by 4 into cos c. Okay. Now similarly for sin phi, if you do this for sin phi, similarly if you do then you can write like this, power of sin phi is minus infinity to plus infinity d phi sin phi e to the power minus phi minus phi naught whole square by 4 drt 4 drt into 1 by root over of 4 pi drt. So similarly, you can write this as sine b phi prime c. So similarly, 1 by root over of 4 pi drt into minus infinity to plus infinity b d phi prime sine b phi prime plus c into e to the power minus phi prime square bar, where phi prime is equal to phi minus phi naught divided by 4 drt, and b is root over of 4 drt. That is what we have written in terms of this. Okay, now doing the similar thing, it will fetch, if you follow the same path, then it will be sine b phi prime c will give you sine b phi prime cos c plus cos b phi prime sin c. Now this is odd function and this is even function. Now since sine b phi prime is a odd function of phi prime, so integrating over it makes the integral vanish. This will go 0, so only this term is contributes, so only thing contributes this term, and then this gives the following term. First is b sin c into root pi to the power minus b square by 4 into 1 by 4 pi drt to the power half. So to the power half, where b is root over of 4 drt and c is equal to phi naught. So now using this, you will get c is phi naught, so this is, using this you will get then b is root over of 4 drt sine phi naught into root pi into e to the power minus drt into 1 by 4 pi drt into root. So this cancels out and it remains sine phi naught into e to the power minus drt. So only thing that comes out to be, so this thing. Okay, so basically let's summarize what we have got so far. So we have got average of cos phi giving you cos phi naught e to the power minus drt, and average of sin phi is giving you sin phi naught e to the power minus drt. Okay, okay, so now we got this. Now we should write the autocorrelation function. So let's evaluate. Now let us evaluate this cos phi 1 cos phi 2. Now if we got this, then we can easily, so if you got this, you can easily calculate the mean square displacements. So to get this, what we will do, we will write the following thing. First, cos phi 1 cos phi 2 will be minus infinity to plus infinity d phi 1 and minus infinity to plus infinity d phi 2 cos phi 1 cos phi 2 2, and then phi 2, let's say transition probability from phi 1 at t1 to phi 2 at t2, and phi 1 t1 from phi naught t naught. This is the probability, right? Okay, so basically we will get now, if you take this guy, this will become, so we can do two things. What we can do is we can write cos phi 1 cos phi 2 in terms of this, and we can get this. So now if you keep this fixed, and if you do the integration of this guy, then sorry, or if you take this and if you do this, then that becomes the integration of d phi 1 phi 1 minus infinity to plus infinity d phi 2 cos phi 2, and this one will be e to the power minus phi 2 minus phi 1 whole square by 4 dr t2 minus t1 into 1 by 4 pi dr t2 minus t1. Okay, so similar previous thing, only thing is here the constant term phi 1 is replaced, phi naught is replaced by this, so then this becomes then cos phi 1 e to the power minus dr t2 minus t1. Only thing is this is constant, so using this formula like this. Okay, now put this value back into this, then this becomes cos phi 1 cos phi 2, that becomes minus infinity to plus infinity d phi 1 cos phi 1, and from this marked part becomes cos phi 1 e to the power minus dr t2 minus t1 e to the power minus phi 1 minus phi naught whole square divided by 4 dr t1 into 1 by 4 pi dr t1 root. Okay, so then it becomes minus infinity, then this becomes minus infinity to plus infinity here cos phi 1, so this will be cos phi 1 squared, so cos phi 1 squared into e to the power minus phi 1 minus phi naught by 4 dr t1 into 1 by root over of 4 pi dr t1. Okay, now this cos phi 1 square, cos phi 1 squared can be written as half of 1 plus cos 2 phi 1. Okay, now for 1 we can easily write, for 1 we will do this. Okay, so if you substitute this thing, then for 1 it becomes minus infinity to plus infinity d phi 1 times there was 1. Okay, so I will take half outside, we will multiply it later. Phi 1 into e to the power minus phi 1 minus phi naught whole square divided by 4 dr t1 into 1 by root over of 4 pi dr t1. So this is standard Gaussian integral, that becomes 1, and on the other hand this thing minus infinity to plus infinity d phi 1 cos 2 phi 1 e to the power minus phi 1 minus phi naught whole square by 4 dr t1. This is 1. This is, we have seen this kind of integral in this thing. So here you can write the whole thing as, let's say, take a is equal to root over of 4 dr t1 and phi prime as phi 1 minus phi naught into root over of 4 dr t1. Okay, then substitute this here. This becomes, then substituting it, it becomes minus infinity to plus infinity a d phi prime cos of 2 phi 1 means b phi prime plus phi naught, twice of that, e to the power minus phi prime square times 1 by root pi into a. Okay. Okay, so this is a cos general form cos bx plus c, and so this was the general term cos bx plus c, where bx is 2b phi. So if you write that, then it becomes, so using this general form of this, so if you write that, then it becomes root pi times e to the power minus, so this is, for this is 2b, so 2b whole square by 4 into cos 2 phi naught into a into 1 by root pi into a cancels out, root pi cancels out, only thing remains is b is equal to a, b is equal to a, only thing remains is e to the power minus b square cos 2 phi naught, that becomes to the power minus 4 dr t1 cos 2 phi naught. Now put this value, this expression will get the exact expression as clubbing all these expressions into one, we will get we will get we will get cos phi t1 cos phi t2 is equal to half, and for it was 1, so this will be 1, and for this was this, so cos 2 phi naught e to the power minus 4 dr t1 times sorry, there was this term also there, power minus tr t2 minus t1. So if you put this becomes a to the power minus tr t2 minus t1. So this is the grand expression, let's say a. Okay, so we have got these correlations cos phi t1 cos phi t2, and I will stop here. In the next class we will uh, look into the autocorrelation of sin phi t1 and sin phi t2, and we will then get the cos phi t1 cos phi t2 and sin phi t1 sin phi t2, and we'll put them back in the expressions to get the exact mean square displacement. Okay, so I will stop here.